Right now, somewhere in the southern sky, buried inside one of the most violent galaxy clusters ever detected, there is a black hole so massive that it breaks the language we use to describe it. Its estimated mass is 100 billion times the mass of our Sun. Not 100 million, not 100 billion in the way people casually throw around the word billion when describing government budgets or corporate valuations. 100 billion individual stars like our Sun, each one a nuclear furnace burning for billions of years, each one capable of sustaining entire planetary systems, compressed into the gravitational dominion of a single object whose event horizon alone could swallow our entire solar system and continue expanding outward into the void beyond. Scientists call it Phoenix A, and if the estimates are correct, it sits at the theoretical ceiling of how large any black hole can ever become in this universe. But the terrifying part is not its size. The terrifying part is not the event horizon that spans thousands of times the distance between the Earth and the Sun, or the gravitational influence so profound that it rivals the total stellar mass of an entire galaxy. The terrifying part is what Phoenix A's existence reveals about the fragility of our confidence when black holes reach scales this extreme. Because the number 100 billion solar masses is not a measurement in the way that scientists mean when they say they have measured something. It is an estimate, a sophisticated, physically motivated, carefully constructed estimate derived from modeling rather than from direct observation. And the gap between an estimate and a measurement, at these scales, in these environments, across these distances, is wider and more unsettling than almost anyone outside the field of astrophysics fully appreciates. That gap is what this story is really about. If you enjoy journeys that push into the most extreme corners of the observable universe, journeys that do not flinch from the places where human understanding begins to thin and the ground beneath our certainty starts to shift, do me a small favor and hit that like button and subscribe. It genuinely helps this channel reach more people, and it means we get to keep exploring together. Now, get yourself comfortable. Let's begin. You already know what a black hole is, or at least you think you do. You have heard the description repeated so many times, across so many documentaries and textbooks and late-night conversations, that the words have become almost automatic. A region of space where gravity is so intense that nothing, not light, not radiation, not information of any kind, can escape once it crosses a boundary called the event horizon. You have seen the animations, the swirling disk of superheated gas glowing orange and white against the darkness, the dark circle at the center where light bends and warps and finally surrenders. You have absorbed the vocabulary, singularity, accretion disk, spaghettification. These words have entered popular culture so completely that black holes feel almost familiar now, almost safe, like a predator behind thick glass at a zoo. You can observe it, study it, feel the comfortable thrill of proximity to something dangerous, knowing it cannot reach you. That familiarity is a trap, because the black holes most people picture when they hear the term are small. Cosmically speaking, they are trivial. A stellar mass black hole, the kind born when a massive star exhausts its nuclear fuel and collapses in a catastrophic implosion, might weigh somewhere between 5 and 30 times the mass of our Sun. By human standards, this sounds enormous. Our Sun contains 99.8% of all the mass in the solar system. It outweighs Earth by a factor of 333,000. A black hole weighing 10 solar masses is not something to be dismissed, but in the architecture of the cosmos, it is a footnote, a period at the end of a stellar sentence. Now multiply that mass by 1,000,000. You have just entered the regime of supermassive black holes. These are the objects that anchor the centers of galaxies, not some galaxies, not particularly unusual galaxies. Essentially all large galaxies that astronomers have examined closely enough to harbor one of these gravitational engines in their core. They range in mass from roughly 100,000 solar masses at the lighter end to billions, and, in the most extreme cases, tens of billions at the heavier end. They are not accidents or anomalies. They appear to be a fundamental feature of how galaxies form and evolve, growing alongside their host galaxies across cosmic time, in a relationship so intimate and so consistent that the mass of a black hole can be predicted from the properties of the galaxy surrounding it, and vice versa. Our own galaxy hosts one. It is called Sagittarius A-star, and for decades, it was the closest supermassive black hole astronomers could study in meaningful detail. Close, in cosmic terms, meaning 26,000 light-years away. Close meaning the light you would need to see it. Left its source before our ancestors had developed agriculture, before the first cities rose along the Tigris and Euphrates, before written language existed, before any record of human civilization begins. And yet, in the context of a universe 13.8 billion years old and 93 billion light-years across, in the observable portion alone, 26,000 light-years is practically next door. The mass of Sagittarius A-star has been measured with extraordinary precision, not estimated, not inferred from scaling relations, measured in the most direct sense that astrophysics allows, by watching individual stars trace their orbits around the invisible central mass. For decades, two independent research groups, one led by Andrea Ghez at the University of California, Los Angeles, the other by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, pointed their telescopes at the chaotic, dust-shrouded heart of the Milky Way and tracked the motions of individual stars in the central cluster. This work required patience measured not in months but in years, decades. The stars close to Sagittarius A-star move fast by stellar standards, completing full orbits in timescales short enough for a human lifetime to encompass. A star designated S2 completes one full orbit around the central mass in approximately 16 years. By observing S2 and dozens of other stars across multiple complete orbital periods, watching them swing inward, accelerate, pass periapsis at tremendous speed, and arc back outward, the teams could apply the same Keplerian mechanics that Kepler himself used to describe the motions of planets around our Sun. The equations are not exotic. They are 400-year-old geometry. Applied to stars orbiting a black hole 26,000 light-years away, they produced a number, approximately 4 million times the mass of our Sun. Ghez and Genzel shared the Nobel Prize in Physics in 2020, in part for this work. 4 million solar masses. Let that number settle into something physical. Take every planet in our solar system, Jupiter, with its crushing gravity and its storms the size of Earth. Saturn with its rings spanning nearly 3 times the planet's diameter. Uranus and Neptune out in the frozen darkness where sunlight arrives so diluted it barely warms the surface. Add all of it together with every moon, every asteroid, every comet drifting through the outer reaches of the Oort cloud, and you get roughly 1% of the Sun's mass. 1%. Now, take the Sun and multiply it by 4 million. That object, that unimaginable concentration of mass, sits at the center of our galaxy right now. It has always been there. It was there when the first humans looked up at the Milky Way and wondered what lay beyond the stars. It will still be there when the Sun exhausts its fuel in approximately 5 billion years and swells into a red giant that engulfs the inner planets. But here is the thing that most people's intuition about black holes never quite reaches. Sagittarius A-star is not large. By the standards of what astronomers have found elsewhere in the universe, it is modest. It is almost unremarkable. Compared to the objects at the true extreme end of the mass scale, our galaxy's central black hole is what 4 million is compared to 100 billion, a rounding error, a decimal point, a grain of sand set against a beach that stretches beyond the horizon in every direction. To reach the objects that live at that extreme end, we need to climb, and the first significant rung on that ladder is an object that forever changed how humanity thinks about black holes, not because of its mass alone, but because of a single photograph. In April of 2019, the Event Horizon Telescope collaboration released something the world had never seen before. Not an illustration, not a computer simulation, an actual image. A real photograph, assembled from data collected by a network of radio telescopes positioned across the entire surface of the Earth, from Hawaii to Chile to Spain to Antarctica, functioning together as a single instrument with a resolving power equivalent to a telescope the size of our planet. The target was the supermassive black hole at the center of a galaxy called Messier 87, located approximately 55 million light-years away in the Virgo cluster. The image showed a bright ring of superheated plasma surrounding a dark shadow at the center. That shadow was the silhouette of the event horizon set against the glowing accretion material orbiting just outside it. It was blurry by the standards of everyday photography. It was orange and asymmetric, and not particularly dramatic to eyes trained on high-resolution images from the Hubble Space Telescope. But what it represented was staggering. For the first time in the history of our species, we could see the actual boundary of a black hole, not an artist's impression. The thing itself, rendered in radio waves collected by dishes separated by the full diameter of our planet, processed by algorithms sophisticated enough to reconstruct an image from the interference patterns of light, arriving at different telescopes at different times. The shadow's diameter, combined with the known distance to Messier 87, allowed an independent measurement of the central mass. The result was approximately 6.5 billion solar masses, consistent with earlier estimates from stellar dynamics. 6.5 billion. If Sagittarius A-star is a house cat, M87 star is a full-grown bull elephant. The event horizon of M87 star spans approximately 38 billion kilometers in diameter. That is larger than the orbit of Pluto. If you placed M87 star where our Sun currently sits, its event horizon would extend past every planet in the solar system and keep expanding outward into the Kuiper belt, past the heliopause, into the interstellar medium beyond. Every world we have ever explored, every target, every space mission has ever visited, every planet that any instrument we have built has ever photographed up close, all of it would sit inside this object's event horizon with room left over. Light, traveling at just under 300,000 kilometers per second, would need approximately 5 days to travel around the circumference of M87 star's event horizon. 5 days for the fastest thing in the universe to complete a single circuit of the boundary of this object. And M87 star is still not the largest. It is not even close to the largest. This is where the story leaves the territory of confirmed measurements and enters something more complex, something that requires you to think carefully about what it means to know a number rather than merely to state one. Because above M87 star, above 10 billion solar masses, the ladder continues, but the footing becomes less certain. The measurements grow more difficult, the methods diverge, the objects sit farther away, embedded in environments so extreme that the tools astronomers rely on for nearer, quieter systems begin to strain. The black holes in this range still exist. They are real objects, producing real gravitational effects on real matter surrounding them. But the question of how massive they are, precisely, confidently, reproducibly, is a different question entirely from the one answered by watching stars orbit Sagittarius A-star for 30 years. Astronomers have a name for black holes that exceed 10 billion solar masses. They call them ultramassive. The word itself carries a signal. Supermassive already sounds like the end of a naming convention. Ultramassive sounds like what happens when the convention runs out of runway. But the term exists because the objects it describes occupy a genuinely different regime, not simply bigger versions of M87 star. Objects that live in different environments, grew through different mechanisms, and push against the limits of what our theoretical models predict should be possible. To understand why those limits exist, and why Phoenix A pressing against them is so significant, you need to understand how black holes grow, because they do not simply appear fully formed at their final mass. They accumulate it, and the process of accumulation has natural constraints that act like governors on an engine, preventing the growth from proceeding arbitrarily fast or arbitrarily far. The primary mechanism is accretion. Gas, dust, and disrupted material falls inward under gravity, forming a swirling disk that gradually spirals toward the event horizon. As the material compresses and accelerates, it heats to temperatures of millions of degrees and radiates energy furiously across the electromagnetic spectrum. Some of that energy escapes before the material crosses the horizon and is lost to the black hole forever. The rest falls in, adding its mass energy to the object. Here is the crucial constraint. The more intensely a black hole feeds, the more radiation it produces. That radiation exerts pressure on the infalling gas, pushing outward against the gravitational pull, drawing material inward. At a certain accretion rate, the outward radiation pressure exactly balances the inward gravitational attraction. This balance point is called the Eddington limit, named for the British astrophysicist Arthur Eddington, who first derived it in the early 20th century. Below the Eddington luminosity, gas falls freely. Above it, radiation begins to blow the infalling material away, choking off the fuel supply and slowing the growth. At the Eddington limit, a black hole doubles its mass in roughly 50 million years. Starting from a seed of 1,000 solar masses shortly after the Big Bang and growing continuously at this rate for the full age of the universe, you would arrive at a final mass of somewhere between 50 and 100 billion solar masses. That is the theoretical ceiling, not a hard wall enforced by a single physical law, but a soft upper boundary imposed by the convergence of multiple independent constraints operating simultaneously across cosmic time. 100 billion solar masses. The number that Phoenix A's estimated mass happens to match almost exactly. That coincidence, or confirmation, depending on how much you trust the estimate, is the core of the most unsettling mystery in the study of extreme black holes. And to understand what it means, we need to travel to a galaxy cluster so massive, so luminous, so violently active that when astronomers first detected it in 2010, it stood out immediately as one of the most extreme environments ever catalogued in the observable universe. That cluster is the Phoenix cluster, and what sits at its center may be the most massive black hole humanity has ever identified, or it may not be. And the uncertainty between those two possibilities is precisely where the story becomes genuinely terrifying. In 1957, two Mexican astronomers named Braulio Iriarte and Enrique Chavira were conducting a survey of faint blue stars at the Tonantzintla Observatory in the highlands of Puebla, central Mexico. The observatory sits on a hillside surrounded by volcanic terrain, and its Schmidt telescope was being used to photograph patches of sky away from the dense plain of the Milky Way, searching for white dwarfs and other hot blue objects that would stand out against the cooler stellar background. The work was methodical and unglamorous. Catalogue entry after catalogue entry. Coordinates, magnitudes, color notes. One of the objects they recorded appeared, in their words, decidedly violet. It was faint, unremarkable in every way except its color. They logged it as entry number 618 inches, the Tonantzintla catalogue, and moved on. Nobody paid attention. The object sat in the catalogue for over a decade, a cosmic giant hiding in plain sight, mistaken for a nearby star in our own galaxy, because the conceptual framework needed to understand what it truly was had not yet been invented. Quasars were not identified as a class of objects until 1963, when the Dutch-American astronomer Martin Schmidt sat down with the spectrum of an object called 3C273 and recognized something that had eluded everyone who had looked at similar data before him. The spectral lines were in the wrong places, completely wrong. No known element produced lines at those wavelengths under any laboratory conditions. Schmidt stared at the data for weeks. Then, in what he later described as a sudden, almost physical realization, he understood. The lines were not in the wrong places because the object was chemically unusual. They were in the wrong places because the object was moving away from us at an extraordinary velocity. The lines had been redshifted, stretched toward longer wavelengths by the expansion of space itself, carrying the signature of a source so distant that the universe had expanded significantly since its light was emitted. 3C273 was not a nearby star. It was billions of light years away, and it was still visible. The only way to reconcile that visibility with that distance was to accept that this object was producing energy on a scale that made entire galaxies look dim by comparison. The word quasar, a contraction of quasi-stellar radio source, entered the vocabulary of astronomy, and immediately the floodgates opened. astronomers began re-examining catalogues of unusual blue objects, looking for others that shared 3C273's properties. Entry 618 inches, the unsettling catalogue, with its decidedly violet color and its faint but distinct presence on photographic plates, was exactly the kind of object worth re-examining. In 1970, radio emissions were detected coming from the direction of unsettling 618. Radio emission from a point source far from the galactic plane was a strong signal. This was not a white dwarf drifting quietly through our galaxy. Shortly afterward, Marie-Helene Ulrich at the McDonald Observatory in Texas obtained optical spectra of the object and confirmed what the radio data had suggested. TON 618 was a quasar, and its redshift placed it at a distance that stopped the breath. The light reaching Earth from TON 618 had been traveling for approximately 10.8 billion years. The object existed when the universe was barely 3 billion years old, when the large-scale structure of the cosmos was still assembling itself, when the first massive galaxies were only beginning to consolidate from the primordial web of dark matter and gas. Despite that almost incomprehensible remove in time and space, TON 618 was visible. Not merely detectable by the most sensitive instruments available, visible as a distinct point source in survey images taken with a modest Schmidt telescope in Mexico. The only way that is possible is if TON 618 was producing energy on a scale that belongs in a different category of description entirely. The numbers confirm it. TON 618 has an absolute magnitude of roughly -30.7, making it one of the most luminous objects ever detected in the observable universe. Its total power output is estimated at approximately 5 × 10⁻40 watts. To translate that into terms that carry any weight at all, TON 618 shines with the luminosity of approximately 140 trillion suns. Not 140 billion, 140 trillion, 140 million individual stellar furnaces, each one burning nuclear fuel for billions of years, each one capable of sustaining an entire planetary system. You would need every single one of them burning simultaneously at full intensity to match the energy output of this single object. Consider what that luminosity means at its true distance of 10.8 billion light-years. After the vast majority of its light has been diluted by the expansion of space across most of the observable universe, after photons have spent over 10 billion years traveling through a cosmos that has been stretching in every direction the entire time, TON 618 is still detectable. It was detectable on photographic plates 50 years before astronomers had the conceptual framework to understand what they were seeing. That is the kind of luminosity we are dealing with. Not bright, not very bright. Bright enough to be seen across the majority of the observable universe with equipment designed to photograph faint nearby stars. That energy comes from one source. The supermassive black hole at the center of TON 618 is feeding. Gas, dust, and disrupted stellar material are spiraling inward through an accretion disk, compressed and heated to temperatures of millions of degrees by friction and the conversion of gravitational potential energy into radiation. The accretion disk around TON 618 is one of the most energetic environments in the known universe. A maelstrom of superheated plasma orbiting at significant fractions of the speed of light, radiating across the entire electromagnetic spectrum with an efficiency that dwarfs the nuclear fusion powering ordinary stars. While nuclear fusion in stellar cores converts roughly 0.7% of mass into energy, accretion onto a black hole can achieve efficiencies of 5 to 40% depending on the spin of the object. At the luminosities exhibited by TON 618, the central engine is converting infalling matter into radiation with an efficiency that ranks among the highest known in nature. The brilliance of TON 618 is both its gift and its curse for astronomers trying to study it. The quasar's glare is so intense that it completely overwhelms the light from the host galaxy surrounding it. Every quasar lives inside a galaxy. The black hole did not form in empty space. It grew inside a galactic structure, fed by that structure's material, shaped by its merger history, embedded in its stellar mass. But in the case of TON 618, The quasar outshines its host so completely that the galaxy itself is invisible to us. We know it must be there, we cannot see it. We see only the blazing engine at its core, surrounded by nothing but the glare of its own excess. This invisibility of the host galaxy has direct consequences for the question of mass. One of the most powerful methods for estimating the mass of a supermassive black hole in a distant active galaxy is a technique called reverberation mapping. The logic is elegant. The quasar's central engine varies in brightness over time, flickering as the accretion rate fluctuates. These brightness variations propagate outward at the speed of light, illuminating clouds of gas orbiting at various distances from the black hole. Those gas clouds respond to the changing illumination by brightening and fading in turn, but with a time delay that corresponds to the light travel time between the central engine and the clouds. By measuring this time delay and combining it with the velocity of the gas clouds, derived from the width of their spectral emission lines, astronomers can calculate the mass enclosed within the orbit of those clouds. The time delay gives the distance. The velocity gives the orbital speed. Together they give the mass. It is less direct than watching individual stars trace full orbital paths around a central object, as was done for Sagittarius A-star. But it is grounded in the actual measured velocities of actual observed material moving under the gravitational influence of the black hole. It is observational, not merely modeled. For TON 618, the key spectral lines used to estimate the black hole's mass come from the broadline region, a zone of fast-moving gas clouds relatively close to the central engine, orbiting at distances measured in light weeks to light months. These clouds move fast because they are close and because the gravitational field pulling on them is intense. The width of their emission lines, the spread of wavelengths across which each line is detected, encodes the distribution of velocities in the gas. Wider lines mean faster velocities. Faster velocities mean stronger gravitational pull. Stronger gravitational pull means more mass. The original mass estimate for TON 618's black hole came from work by Ohad Shemer and colleagues, who measured the width of the hydrogen beta emission line for a sample of 29 quasars, including TON 618. The hydrogen beta line is a specific wavelength of light emitted by hydrogen atoms in the broadline region. It is one of the most commonly used tracers of gas velocity in quasar spectroscopy. In TON 618's spectrum, the hydrogen beta line was found to be unusually broad, with velocity measurements suggesting gas moving at speeds reaching approximately 10,500 kilometers per second. These were among the highest velocities measured in any quasar in the sample. The mass derived from these measurements was approximately 66 billion times the mass of our Sun. 66 billion. For years, this number circulated through the popular science landscape as the definitive answer to the question of the most massive black hole ever found. Documentaries featured it. Infographics compared its event horizon to the solar system. Science communicators cited it as the ultimate example of gravitational excess. Even the Guinness World Records listed TON 618 as the most massive observed black hole, cementing its place in public consciousness as a settled fact, a record written in ink. Then, in 2019, a study by Greer and colleagues reanalyzed the spectral data using a different emission line. Instead of hydrogen beta, they used the carbon IV line, an alternative spectral feature produced by triply ionized carbon atoms, a different species of gas that does not necessarily occupy the same region of space around the black hole as the hydrogen responsible for the hydrogen beta emission. These two gas populations may orbit at different distances, experience different physical conditions, and respond differently to the quasar's radiation field. The carbon IV line yielded a lower velocity measurement of approximately 2,761 kilometers per second, with an uncertainty of 423 kilometers per second. This lower velocity translated directly into a lower mass estimate of approximately 40.7 billion solar masses. 40.7 billion. Still enormous. Still among the most massive black holes known. Still larger than the total stellar mass of the Milky Way. which contains somewhere between 50 and 64 billion solar masses worth of stars, but significantly lower than the original 66 billion. The revision did not dethrone TON 618 from the upper ranks, but it demonstrated something important about the fragility of these measurements. Two estimates, derived from the same observational data, the same quasar, the same telescope observations, differed by 25 billion solar masses. The difference came entirely from which spectral line was chosen to trace the gas velocities and how the physics of that line was interpreted. This is not a scandal. It is a well-known challenge. Different emission lines form at different distances from the central engine under different physical conditions. The hydrogen beta line and the carbon IV line do not trace the same population of gas clouds. The carbon IV line in particular is known to be influenced by forces other than gravity, most significantly by radiation pressure. At the luminosities exhibited by TON 618, the radiation pouring from the accretion disk is not merely illuminating the surrounding gas, it is pushing it. Photons carry momentum. When they strike gas clouds or are absorbed by them, they transfer that momentum, accelerating the gas outward. This radiation pressure adds velocity to the gas that has nothing to do with gravity. And because the mass estimate depends on interpreting the gas velocity as a measure of gravitational pull, any additional velocity from radiation pressure inflates the apparent mass. Think of it this way. You are trying to determine the weight of a swimmer by measuring how fast they move through water, but the swimmer is also being pushed by a current. The current adds speed that has nothing to do with the swimmer's own strength. Your measurement of speed will overestimate their strength unless you can precisely subtract the current's contribution. At moderate quasar luminosities, the radiation pressure effect is small and manageable. At the extreme luminosities of TON 618, it may be significant enough to bias the mass estimate substantially. The earthquake is shaking the scale. The consequence is straightforward and uncomfortable. The mass of TON 618's black hole is not a single number. It is a range, somewhere between roughly 40 billion and 66 billion solar masses, with different analyses favoring different points within that range, and with the true value depending on physical effects that are difficult to disentangle at a distance of 10.8 billion light-years. To feel what that range means physically, consider both ends of it as actual objects in space. At 40.7 billion solar masses, the lower estimate, the event horizon of TON 618's black hole already spans a radius of approximately 800 astronomical units. 1 astronomical unit is the distance from the Earth to the Sunday. The orbit of Pluto sits at roughly 40 astronomical units from the Sunday. The event horizon of TON 618, at its lower estimated mass, extends 20 times farther than the orbit of Pluto in every direction from its center. If you placed this black hole where our Sun currently sits, everything you have ever known about the solar system would vanish inside it instantly. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, the entire Kuiper belt, all of it consumed, with the event horizon still expanding outward through the scattered disk and into the interstellar void beyond. At 66 billion solar masses, the original higher estimate, the event horizon grows to a radius of approximately 1,300 astronomical units, more than 30 times the distance from the Sun to Pluto. Light now needs nearly 7 weeks to complete a single circuit of its circumference. Voyager 1, the most distant human-made object ever launched, traveling continuously since 1977 and now sitting at approximately 60 astronomical units from the Sun after nearly 5 decades of flight, would still be deep inside this event horizon. It would need to travel more than 20 times farther just to reach the edge. The gap between these two estimates, the physical difference between a black hole of 40 billion solar masses and one of 66 billion, is itself a volume of space larger than our entire planetary system. That gap exists not because anyone made a mistake, but because the same quasar looks different depending on which spectral line you choose to read it with. And then there is the environment that TON 618 has sculpted around itself, because the black hole does not exist in isolation. In 2021, observations by the Atacama Large Millimeter Array revealed that TON 618 is surrounded by an enormous cloud of gas classified as a Lyman alpha blob, a vast nebula of hydrogen glowing in ultraviolet light under the quasar's intense radiation. This nebula spans at least 100 kiloparsecs in diameter. 100 kiloparsecs is approximately 330,000 light-years. The Milky Way is roughly 100,000 light-years across. The gas structure surrounding TON 618, not the black hole itself, not the accretion disk, not the host galaxy, but merely the illuminated cloud of hydrogen enveloping the system, is more than 3 times the diameter of our entire galaxy. Within this nebula lie 2 components: an inner molecular outflow driven by the black hole's jets, and an extended cold molecular gas reservoir in the surrounding intergalactic medium, each containing approximately 50 billion solar masses of material. Both components are aligned with the powerful radio jets produced by the central black hole. This alignment is not coincidental. It records the black hole's history. The jets have been driving material outward, shaping the gas distribution across hundreds of thousands of light-years, regulating the flow of fuel that might otherwise fall inward for a period measured in hundreds of millions of years at minimum. TON 618's nebula is a fossil record of the black hole's activity, written across a canvas 3 times the size of the Milky Way. This is what an ultramassive black hole looks like when you pull back far enough to see the full extent of its influence. Not just the event horizon, not just the accretion disk, the entire sculpted environment stretching across a region that would dwarf our galaxy the way a city dwarfs a single room. And yet, even with that context, even with the revised mass estimates and the radiation pressure complications and the spectral line debates, TON 618 remains the most observationally grounded of the extreme black hole candidates. Its mass may not be known precisely, but the range is constrained by real measurements of real gas moving at real velocities under the influence of a real gravitational field. The uncertainties are significant, but they are uncertainties within a fundamentally observational framework. When astronomers need a reliable anchor for discussions of ultramassive black holes, TON 618 is the name they reach for. Not because it is the largest, but because the evidence for its extreme mass is the most directly observational evidence available for any object in this mass range. Phoenix A may be larger. The estimates say it is, but the nature of those estimates, what they rest on, what they assume, and how far they sit from direct observation is a fundamentally different story. And that story begins in Antarctica. In 2010, a team of astronomers pointed the South Pole telescope at the southern sky and detected something that immediately stood out from everything around it. The South Pole telescope is a 10-meter radio telescope sitting at the Amundsen-Scott South Pole Station in Antarctica, one of the most inhospitable places on the surface of this planet. It was placed there deliberately. The cold, extraordinarily dry atmosphere above the geographic South Pole is nearly transparent to the millimeter wavelength radiation the telescope was designed to detect, making it one of the best locations on Earth for this particular kind of observation. Its primary mission was to survey large patches of sky for galaxy clusters, using a phenomenon called the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background radiation caused by hot gas inside massive clusters when photons from the early universe pass through the superheated gas, filling the interior of a galaxy cluster. Some of them gain energy from collisions with the fast-moving electrons in the gas. This shifts the photons to slightly higher frequencies, leaving a faint but detectable imprint on the background radiation that permeates all of space. The effect is small. Detecting it requires extraordinary sensitivity, but when a cluster is massive enough and its gas is hot enough, the signal becomes unmistakable. The signal from the Phoenix cluster was unmistakable. Located in the constellation Phoenix, roughly 5.7 billion light-years from Earth, this cluster immediately distinguished itself in the survey data. Williamson and colleagues reported the initial detection, and follow-up observations across multiple wavelengths quickly revealed why the signal had been so striking. The Phoenix cluster is one of the most massive galaxy clusters ever discovered, weighing in at approximately 2 quadrillion solar masses. That is 2 times 10 to the 15th power. A number so large that writing it out in full requires 16 digits. To place that in perspective, the Milky Way, including its dark matter halo, weighs roughly 1.5 trillion solar masses. The Phoenix cluster outweighs our entire galaxy by a factor of more than 1,000. It is a gravitational colossus, one of the heaviest gravitationally bound structures the universe has ever assembled in the observable portion of the cosmos. But mass alone was not what made the Phoenix cluster remarkable. The Phoenix cluster is also the most luminous X-ray cluster ever detected. It pours out more X-ray radiation than any other known galaxy cluster in the observable universe. The hot gas filling the space between its galaxies, the intracluster medium, reaches temperatures of tens of millions of degrees, superheated by the gravitational energy released as matter falls into the cluster's enormous gravitational well over billions of years. This gas does not sit passively in the darkness between galaxies. It glows with ferocious intensity in X-ray wavelengths, radiating energy at a rate that eclipses every other galaxy cluster astronomers have measured. X-ray observations from the Chandra Space Observatory revealed the structure of this superheated gas in extraordinary detail. The gas fills the cluster like a luminous fog, densest at the center, where the gravitational pull is strongest, and thinning gradually toward the outskirts, where the density and temperature taper away. Near the core, something unusual is happening. The gas is cooling, not gently, not at the slow measured pace seen in most clusters, where the central black hole maintains equilibrium. It is cooling catastrophically, at one of the highest rates ever recorded in any galaxy cluster anywhere in the observable universe. Approximately 3,000 to 4,000 solar masses of material per year are condensing out of the hot phase, losing their energy, and becoming available to collapse inward under gravity. To understand why this is remarkable, and why it is the key to the entire Phoenix A story, you need to understand how this process is supposed to be prevented. In most massive galaxy clusters, the central black hole functions as a thermostat. As the hot intracluster gas gradually radiates away its energy, it cools and begins to flow inward toward the center of the cluster. This inflow provides fresh fuel for the central black hole, which responds by accreting more material and launching more powerful jets. Those jets, streams of relativistic plasma, ejected along the black hole's rotational axis at velocities approaching the speed of light, slam into the surrounding intracluster gas and inflate enormous cavities, bubbles of low-density plasma that push the hot gas aside and deposit their energy into the surrounding medium. The gas is reheated. The cooling is interrupted. The inflow slows. The black hole's feeding rate drops. The jets weaken. The gas begins to cool again, and the cycle repeats, a self-regulating loop that has been maintaining approximate thermal equilibrium in galaxy cluster cores for billions of years. Across the majority of the clusters, astronomers have studied closely. The best studied example of this thermostat working correctly is the Perseus cluster, one of the brightest X-ray clusters in the sky, and one of the most thoroughly examined objects in extragalactic astronomy. At the center of Perseus sits the giant elliptical galaxy NGC 1275, which harbors a supermassive black hole, actively feeding and launching powerful jets of relativistic plasma into the surrounding medium. Chandra X-ray images of the Perseus cluster reveal the consequences of this activity in stunning detail. Dark voids in the X-ray emission surrounded by bright rims of compressed gas, each cavity tens of thousands of light years across. They look like blisters pressed into the fabric of the cluster's atmosphere, ghostly impressions of the black hole's power, written into the surrounding gas as physical depressions where the jets have pushed the hot medium aside and deposited their energy. The energy budget in Perseus is roughly balanced. The amount of energy the jets deposit into the surrounding gas approximately matches the rate at which that gas would otherwise cool and collapse. The black hole heats the gas. The gas stays hot. Fresh fuel struggles to reach the center. Star formation remains suppressed. The central galaxy sits red and quiet, dominated by old stars with very little new stellar birth occurring. This equilibrium has been maintained for hundreds of millions of years, possibly billions. The thermostat works. The Phoenix cluster proved that this thermostat can fail. Phoenix A's central black hole is not absent. Radio observations confirmed the presence of relativistic jets extending outward from the core. X-ray images revealed cavities in the intra-cluster gas, the same kind of imprints seen in Perseus, evidence that the black hole is producing feedback, that the thermostat mechanism exists and is running. But in the Phoenix cluster, the machinery is losing. The cooling flow is so intense, so overwhelming in the sheer rate at which it is shedding energy, that the jets cannot compensate. The energy being deposited by the black hole's feedback is vastly insufficient to offset the energy being radiated away by the cooling gas. The furnace is burning. The building is losing heat faster than the furnace can replace it. The multi-wavelength study by M. McDonald and colleagues quantified this in extraordinary detail. Their measurements showed a cooling rate of roughly 3,820 solar masses of material per year falling out of the hot phase and becoming available to collapse, among the highest cooling rates ever observed in any cluster core. The team noted that the feedback mechanism expected to prevent runaway cooling appeared to be fundamentally inadequate to balance the radiative losses in this system. In their framing, the Phoenix cluster was a system where the feedback loop had either not yet fully established itself or had been catastrophically overwhelmed by the sheer intensity of the cooling flow. The consequences of this failure are visible across the entire central galaxy. Because the gas is cooling faster than feedback can prevent, enormous quantities of cold, dense material are raining down onto the central galaxy, collapsing under gravity and igniting into new stars at a rate that has no close parallel in any other galaxy cluster core in the observable universe. The central galaxy of the Phoenix cluster was forming new stars at approximately 740 solar masses per year at the time of the observations. For comparison, the Milky Way forms new stars at a rate of roughly 1 to 2 solar masses per year. Phoenix A's central galaxy was manufacturing new stars approximately 500 times faster than our entire galaxy. This is one of the most extreme starburst rates ever measured anywhere in the universe, let alone at the center of a galaxy cluster, and it stands in stark contrast to the quiet, red, star formation suppressed central galaxies that dominate essentially every other massive cluster astronomers have examined closely. 740 solar masses of new stars per year. Picture what that means. Every year, the central galaxy of the Phoenix cluster adds enough new stellar material to create 740 objects like our Sun, each one a nuclear furnace beginning a lifetime measured in billions of years, each one potentially capable of sustaining planetary systems of its own. While the Milky Way quietly assembles 1 or 2 new suns over the same period, Phoenix A's host galaxy is building a small stellar population, not a modest increment. A continuous, ferocious, almost uncontrolled explosion of stellar birth driven by the collapse of gas that the broken thermostat could not prevent from cooling. But here is the detail that connects the broken thermostat directly to the mass of the central black hole. The gas does not only form stars, some of it, inevitably, spirals further inward toward the very center of the galaxy and feeds the black hole directly. Estimates suggest that Phoenix A's black hole accretes somewhere in the range of 60 solar masses of material per year, a feeding rate that, sustained over the billions of years the cluster has been in this state or in states of comparable activity, would build an object of extraordinary proportions. The cooling flow is not just a star factory. It is a black hole feeding mechanism operating at a scale that essentially no other environment in the observable universe provides. And if the feeding has been sustained for long enough, the black hole at the center of this catastrophically cooling cluster should have grown to a mass that reflects that sustained excess. This was the reasoning that led a team of researchers to attempt something ambitious. Rather than measuring the mass of Phoenix A's central black hole through direct observation of stellar orbits or gas velocities, which is extraordinarily difficult for an object 5.7 billion light-years away, a team led by M. Brockamp and colleagues built a theoretical model of the black hole's growth. based on the observable properties of its environment and host galaxy. The approach begins with detailed observations of how the stars in the central galaxy are distributed, how their density changes as you move from the outskirts of the galaxy inward toward the core. This stellar density profile encodes information about the gravitational potential at the center of the galaxy, which in turn is influenced by the mass of the central black hole. A more massive black hole alters the orbits of stars in the central region in predictable ways. It pulls them inward, compresses the density profile at the core, and leaves a gravitational imprint on the stellar distribution that, if you know what to look for, can be read backward to infer the mass causing it. By measuring this profile in detail and comparing it to theoretical predictions for different black hole masses, you can estimate how massive the central object must be to produce the observed distribution. This technique is well established in the study of black hole growth in massive galaxies. It has been tested on nearer, better characterized systems and has produced results broadly consistent with more direct measurements where those are available. But Brockamp's method went further than simply reading the stellar density profile. It incorporated the entire feedback relationship between the black hole's energy output and the behavior of the intracluster gas, building a model of how the black hole may have grown over time by accreting material from the cooling flow, tracking the interplay between accretion, feedback, and the evolving thermal properties of the cluster's hot gas reservoir. By adjusting the parameters of this model until the outputs match the full suite of observed properties, the stellar density, the gas cooling rate, the X-ray luminosity, the radio cavities, the starburst rate, the team arrived at an estimate for the black hole's current mass. The result was staggering. The models indicated a central black hole with a mass on the order of 100 billion solar masses, possibly exceeding that value, though the authors noted clearly that the black hole's mass had not been measured through direct dynamical observation of orbiting matter. 100 billion, not 100 million, not the merely enormous billions of M87 star or the tens of billions attributed to objects like TON 618. 100 billion times the mass of our Sun, concentrated into the gravitational dominion of a single object at the center of an already catastrophically extreme galaxy cluster. To feel the physical reality of that number, you need to build the event horizon in your mind and then place it against something familiar. For a non-rotating black hole, the radius of the event horizon is determined directly by the mass through a quantity called the Schwarzschild radius. Double the mass, double the radius. For a black hole of 100 billion solar masses, the Schwarzschild radius works out to approximately 295 billion kilometers. The diameter of the event horizon is therefore roughly 590 billion kilometers. In units that carry more meaning, that is approximately 4,000 astronomical units from one side to the other, 4,000 times the distance from the Earth to the Sunday. Let that image build. Our solar system, Mercury orbiting the Sun at roughly 0.4 astronomical units, close enough that a year there lasts only 88 Earth days. Venus, Earth, Mars out at 1.5 astronomical units, Jupiter at 5, Saturn at 10, Uranus and Neptune at 19 and 30, Pluto at roughly 40 astronomical units, so distant that sunlight takes over 5 hours to reach it, so cold that nitrogen freezes on its surface. The event horizon of Phoenix A's central black hole, if the estimate is correct, stretches to 4,000 astronomical units. It reaches 100 times farther than the orbit of Pluto in every direction from its center. It does not stop at Pluto. It extends outward through the Kuiper belt, past the heliopause where the solar wind finally surrenders to interstellar space, past the inner edge of the Oort cloud, that vast spherical reservoir of icy bodies marking the outermost gravitational boundary of our solar system. The event horizon of this black hole would encompass a region of space that no spacecraft humanity has ever built has come close to reaching. Voyager 1, the most distant human-made object ever launched, traveling continuously since 1977 and now sitting at approximately 60 astronomical units from the Sun after nearly 5 decades of uninterrupted flight, would still be deep inside this event horizon. it would need to travel more than 60 times farther just to reach the edge. Every distance record set by human space exploration across the entire history of spaceflight would be swallowed without ceremony, buried inside this object with room enough remaining for dozens of solar systems to orbit unaware. Now, consider the circumference. A circle with a diameter of 590 billion kilometers has a circumference of approximately 1.85 trillion kilometers. Light travels at roughly 26 billion kilometers per day. Dividing the circumference by that daily light travel distance gives approximately 71 days. Light, the fastest thing in the universe, moving at 299,792 kilometers per second, would need more than 2 months to travel around the event horizon of this black hole, not across it, not through its interior, simply around the outside edge. A photon beginning its journey around the equator of this event horizon in early January would not complete the circuit until mid-March. The mass itself resists every comparison you can construct. 100 billion solar masses is approximately 24,000 times the mass of Sagittarius A-star, the black hole at the center of our own galaxy. It is roughly 15 times the mass of M87 star. It exceeds the total stellar mass of the Milky Way. Our galaxy contains an estimated 400 billion individual stars. The total mass of those stars, the accumulated nuclear fuel and ash of 400 billion stellar lifetimes, adds up to somewhere between 50 and 64 billion solar masses. Phoenix A's central black hole, if the estimate holds, outweighs every star in the Milky Way combined by a comfortable margin. Every sun in our galaxy, every red dwarf burning dimly in the darkness for 100 billion years, every massive blue giant that will live for only a few million years before exploding as a supernova, every white dwarf cooling slowly toward absolute zero across unimaginable timescales, every stellar remnant and stellar nursery and double star system in the entire structure of our galaxy, added together, still falls short of the mass concentrated inside this single object's event horizon. Nothing about that comparison is easy to hold in the mind, and yet this is precisely where you must slow down and hold something else in the mind alongside it. Because the number 100 billion solar masses, for all its extraordinary magnitude, is not a measurement. It is a model output. It emerged from a sophisticated theoretical framework fed by real observations, producing a result consistent with those observations under specific assumptions about the physics governing the system. And the word assumptions carries more weight here than it might at first appear. The estimate has not been confirmed through direct dynamical observation of matter orbiting within the black hole's gravitational sphere of influence. At 5.7 billion light-years, the central region of the Phoenix cluster is far too distant for any current telescope to resolve individual stellar motions or map the velocity field of gas in the immediate vicinity of the event horizon. The angular size of the black hole's sphere of influence on the sky, the region where its gravity dominates over the stellar mass of the surrounding galaxy, is too small to isolate with even the most capable instruments available today. There is no image, there is no spectrum of orbiting gas with directly measured velocities. There is no independent verification from a second method that approaches the problem from a completely different direction. There is a model, a good model, a model grounded in real observations and well-established physical principles, but a model nonetheless, and at least one independent assessment has suggested a mass closer to 10 to 20 billion solar masses for the same object, based on different assumptions about the accretion history and the relationship between the black hole and its host galaxy. The discrepancy between these estimates is not a small technical disagreement. It spans nearly an order of magnitude. The gap between 10 billion and 100 billion solar masses is itself larger than the total mass of M87 star. It contains, within its range of uncertainty, several of the most massive black holes ever measured. Both estimates are the products of serious science. Both rest on real data. The disagreement lies entirely in how that data is translated into a mass, through which theoretical framework, under which assumptions about the complex interconnected processes operating simultaneously in one of the most extreme environments in the observable universe. This is the nature of the frontier. And this is exactly why the question of which black hole is the largest is not the simple question it appears to be. Because at this end of the scale, where the objects are farthest away, where the environments are most complex, and where the masses press against theoretical limits that our models may not perfectly capture, the numbers stop being facts and start being estimates. And the estimates, for all their sophistication, carry uncertainties wide enough to contain entire black holes within their error bars. Phoenix A may be the most massive black hole humanity has ever identified. The evidence points in that direction. The logic is coherent. The physical scenario that produced it, a broken thermostat in the most extreme cluster environment known, a feeding rate with no close parallel anywhere else in the observable universe, a mass that has been growing for billions of years with insufficient feedback to slow it, is internally consistent and physically plausible. But plausible is not confirmed, and at 100 billion solar masses, pressing against the theoretical ceiling of black hole growth, the distance between those two words is the most important distance in this entire story. The comparison between Phoenix A and TON 618 is not a comparison between two numbers, it is a comparison between two fundamentally different kinds of knowledge. And the difference between those kinds of knowledge is what makes the question of which black hole is truly the largest, not merely unanswered, but in a precise and uncomfortable sense, unanswerable with the tools currently available to us. Consider what each estimate rests on. TON 618's mass, somewhere between 40 and 66 billion solar masses, depending on which spectral line you trust and how you handle the radiation pressure problem, is derived from direct spectroscopic observation of gas moving in the gravitational field of the black hole. The gas is real. The velocities are measured. The relationship between the velocity of orbiting gas and the mass pulling it inward is grounded in the same Newtonian and relativistic mechanics that has been tested and verified across 4 centuries of physics. The uncertainties are real, and they are significant. The radiation pressure complication is genuine and unresolved. The gap between the hydrogen beta estimate and the carbon IV estimate is large enough to matter, but the foundation is observational. You are looking at something and measuring how fast it moves, and using well-understood physics to calculate what must be holding it there. The chain of inference is short. Phoenix A's mass, approximately 100 billion solar masses, is derived from modeling the growth history of the black hole, using the observable properties of its host galaxy and the surrounding cluster environment. The observations feeding the model are real. The stellar density profile is measured, the cooling rate is measured, the X-ray luminosity is measured, the jet cavities are imaged, but the mass itself is not measured. It is the output of a theoretical framework that takes those observations as inputs and produces a number consistent with them under specific assumptions about how black holes grow, how feedback couples to the surrounding gas, and how the stellar density profile reflects the gravitational influence of the central mass. The chain of inference is longer. Each link in the chain introduces assumptions, and at 5.7 billion light-years, there is no independent check available to verify that the assumptions are correct. This is not a flaw in the science. It is the unavoidable consequence of trying to characterize the most extreme objects in the universe at the greatest possible distances. You work with what the universe gives you, and what the universe gives you at 5.7 billion light-years is not individual stellar orbits or resolved gas velocity maps. It is the integrated light of a galaxy and a cluster, filtered through billions of years of cosmic expansion, from which you must reconstruct the properties of a single object at the center. The scientists doing this work are not unaware of the limitation. It is stated explicitly in their papers, discussed openly at conferences, and debated in the literature. The uncertainty is not hidden, but the uncertainty also does not travel well from the scientific literature to the public conversation. What travels is the number, 100 billion solar masses. And once a number like that enters circulation, it tends to harden into fact in the popular imagination regardless of the caveats attached to it in the original source. To understand why the rankings at this extreme end of the scale are fundamentally unstable, you need to think about what a mass estimate actually is from a statistical perspective. Every mass estimate for an ultramassive black hole is not a single number, but a probability distribution, a range of values centered on a best estimate, with the probability of the true value being near the center higher than the probability of it being far from the center, but with non-negligible probability extending outward across a range that can span tens of billions of solar masses. For TON 618, the probability distribution is centered somewhere around 40 to 66 billion solar masses, with the spread determined by the disagreement between different spectral line analyses and the uncertainties in radiation pressure corrections. For Phoenix A, the distribution is centered around 100 billion solar masses, with a spread determined by the range of theoretical models and the sensitivity of the result to different assumptions about accretion history and feedback efficiency. The independent assessment suggesting 10 to 20 billion solar masses represents a separate analysis that places the center of its own distribution far below the Brockamp estimate, reflecting how different modeling choices can propagate into dramatically different outputs. Now place these distributions side by side and ask which black hole is more massive. If Phoenix A's true mass is near the center of the high estimate and TON 618's true mass is near the center of its range, Phoenix A wins by a comfortable margin. But if Phoenix A's true mass is near the lower end of its uncertainty range and TON 618's true mass is near the higher end of its range, the ordering reverses. Both outcomes are consistent with the available data. Neither can be ruled out with confidence. The question of which is larger does not have a stable answer because the probability distributions overlap, and in some regions of the parameter space they overlap substantially. This is not a problem that will be resolved by collecting more data of the same kind. It requires either fundamentally new observational techniques capable of directly probing the central regions of these objects at their actual distances, or independent measurements using methods so different from existing approaches that their uncertainties are genuinely uncorrelated. Neither of these is available today. The next generation of extremely large ground-based telescopes, the Extremely Large Telescope, currently under construction in the Atacama Desert of Chile, the 30-meter telescope proposed for Mauna Kea, will push the boundaries of angular resolution and sensitivity significantly. But even these instruments will struggle to resolve the sphere of influence of a black hole at 5.7 billion light-years, with the precision needed to directly measure orbital velocities. The problem is not simply one of telescope aperture, it is one of distance, and distance, in this universe, does not yield to engineering on any timescale relevant to the careers of the scientists currently working on these questions. There is a researcher whose work sits at the precise intersection of these questions. Priyamvada Natarajan, based at the Department of Astronomy at Yale University, has spent years approaching the ultramassive frontier, not by trying to determine which specific black hole holds the record, but by asking the more fundamental question that underlies the entire competition. Is there a maximum mass that any black hole in this universe can ever achieve? Her answer, developed across multiple papers with collaborators over more than a decade, appears to be yes. Her research suggests that a natural ceiling exists at approximately 100 billion solar masses. This limit does not arise from a single physical law enacted at a specific moment. It emerges from the convergence of several independent constraints that operate simultaneously and reinforce each other as black holes grow toward the extreme end of the mass scale. The first constraint is the Eddington limit. As a black hole grows, the luminosity required to maintain accretion at the maximum sustainable rate grows proportionally. The radiation it produces pushes outward against the infalling gas with increasing force. Above a certain accretion rate, this radiation pressure overwhelms gravity for the surrounding gas and the feeding chokes off. A black hole can temporarily exceed the Eddington rate through episodes of chaotic super-Eddington accretion, where gas is funneled inward through dense channels that shield it from the radiation. But sustained super-Eddington growth across cosmological timescales is difficult to maintain. The radiation finds its way out. The gas gets dispersed. The feeding episode ends. The second constraint is the decreasing merger rate. Black holes also grow through mergers with other black holes when their host galaxies collide and eventually coalesce. In the early universe, when galaxies were denser and closer together, and the merger rate was high, this was an efficient growth mechanism. But as the universe expanded, galaxies were carried farther apart. The merger rate declined. Two black holes of 10 billion solar masses merging would instantly produce a 20 billion solar mass object without any accretion required, bypassing the Eddington limit for that mass jump entirely. But such mergers require the right pair of massive galaxies to find each other in spiral and eventually bring their central black holes close enough to merge through gravitational wave emission. At late cosmic times, the probability of such events becomes vanishingly small. The third constraint is feedback. As a black hole grows more massive, the energy output of its jets and winds increases. This energy heats the surrounding gas, disperses potential fuel, and makes it progressively harder for new material to cool and fall inward. The more massive the black hole becomes, the more aggressively its own energy output conspires against its continued growth. At some point, the feedback becomes so effective that the black hole essentially starves itself. It cannot attract fresh fuel faster than its own radiation, and jets drive that fuel away. Natarajan's models incorporate all three of these constraints simultaneously and find that the maximum achievable mass converges on roughly 100 billion solar masses across a wide range of assumptions about seed mass, growth history, and feedback efficiency. The ceiling is soft rather than hard. A black hole could in principle exceed it under unusual circumstances. An extraordinarily efficient period of super Eddington accretion, a rapid sequence of major mergers in an unusually dense environment. But significantly exceeding the ceiling would require conditions that are genuinely rare, even by cosmic standards, and no confirmed observation has yet provided convincing evidence that any object has done so. If this ceiling is real, then Phoenix A's estimated mass of 100 billion solar masses places it right at the limit. Not merely among the most massive black holes known, at the absolute boundary of what the universe permits. This is either a remarkable confirmation that nature can push growth precisely to the theoretical maximum, or a sign that the estimate is inflated by modeling assumptions and the true mass is somewhat lower, or a hint that our models of the ceiling itself need refinement to account for physics we have not yet fully characterized. Each interpretation leads somewhere genuinely interesting. Each points toward a different understanding of how the universe manages its most extreme objects, and none of them can be selected with confidence over the others, given the current state of the evidence. Here is what makes this more than an academic exercise in statistical uncertainty. Here is where the story becomes something you can feel. There is a moment in every encounter with extreme scale when the human mind quietly gives up, not with drama, not with panic or confusion. It simply stops converting numbers into meaning. You hear 100 billion solar masses, and the words pass through you like background noise. You nod, you think you understand. But the feeling that accompanied earlier numbers in this story, the gut-level weight you felt when contemplating Sagittarius A-star at 4 million solar masses, the visceral sense of scale, when M87, star's event horizon, was placed against the orbit of Pluto, that feeling has gone silent. The emotional register has flatlined. This is not a failure of intelligence. It is a feature of how human cognition was built. Our ancestors needed to distinguish between 3 predators and 30. They needed to estimate whether a food source would last 1 week or 5. They needed to judge distances of hundreds of meters and masses of tens of kilograms. They did not need to feel the difference between 40 billion and 100 billion of anything. There was never a survival advantage in registering that distinction with emotional weight. The neural machinery for it was never constructed, and now, standing at the frontier of the most extreme objects in the observable universe, we find ourselves in possession of a cognitive instrument calibrated for a world that is immeasurably smaller than the one we are trying to understand. But here is the unsettling symmetry. The difficulty the human mind faces in feeling the difference between 40 billion and 100 billion solar masses mirrors, in a strange and precise way, the difficulty that science itself faces in measuring that difference. The numbers are so large, the objects so distant, the methods so indirect, that the gap between competing estimates can span tens of billions of solar masses without anyone being able to determine with confidence where the truth lies. The human mind goes numb at these scales. The scientific instruments, for all their extraordinary sophistication, begin to blur. Both reach their limits at the same point. Both surrender precision at the same threshold. This convergence is what makes the ultramassive regime uniquely and permanently unsettling. Consider what it would take to resolve the question definitively. You would need to directly observe the motion of matter, stars, or gas within the gravitational sphere of influence of each black hole. For Phoenix A, that sphere of influence subtends an angle on the sky so small that no current or planned telescope can resolve it from a distance of 5.7 billion light-years. For TON 618, the situation is compounded by the quasar's blinding glare, which washes out any possibility of resolving the host galaxy's central dynamics, even if the angular resolution were sufficient. The object is 10.8 billion light-years away. Even the next generation of extremely large ground-based telescopes with mirrors 30 to 40 meters across will struggle to achieve the angular resolution needed to probe these regions directly. This means that for the foreseeable future, possibly for several decades, the masses of the most extreme black hole candidates will continue to depend on indirect methods carrying substantial uncertainties. The uncertainties will shrink incrementally as new data accumulates and analysis techniques improve, but the fundamental challenge will remain. You are trying to weigh the heaviest objects in the universe from the greatest possible distances using proxies rather than direct measurement. The leaderboard will continue to be written in pencil. The rankings will continue to shift as new studies apply different methods, use updated calibrations, or reanalyze existing data with improved models. And this is where the comparison between Phoenix A and TON 618 reveals something that extends beyond either object individually. It reveals a structural feature of how the universe distributes mass at the most extreme scales, and how our methods of measurement interact with that distribution. In the comfortable middle ranges of black hole masses, from a few million to a few billion solar masses, the population is large enough and the measurements are precise enough that the rankings are stable. There are hundreds of well-measured black holes in this range. Their masses cluster in predictable ways around the scaling relations. The error bars are small compared to the gaps between entries on any list. The ordering makes sense, but above 10 billion solar masses, the population thins dramatically. There are perhaps a few dozen serious candidates in this range across the entire observable universe. Each one lives in an unusual environment. Each one is characterized by a different combination of methods. Each measurement carries uncertainties spanning billions of solar masses, and the objects themselves may be separated by mass differences smaller than the error bars on individual measurements. In this regime, ranking becomes statistically meaningless. Saying Phoenix A at 100 billion solar masses is larger than TON 618 at 40 to 66 billion sounds definitive. But when the full uncertainty on both measurements is properly accounted for, the probability distributions overlap enough that no confident ranking is possible. You could reverse the ordering without violating any observational constraint. Both orderings are consistent with the data. The leaderboard, in other words, is not a leaderboard. It is a cloud of overlapping probability distributions, each centered on a best estimate but spreading outward across tens of billions of solar masses of genuine uncertainty. Asking which black hole is definitively the largest is like asking which cloud in the sky is definitively the tallest. The question assumes a precision the data cannot support. And yet this very ambiguity is what TON 618 and Phoenix A considered together illuminate so powerfully. Because even at the lower end of TON 618's mass range, around 40 billion solar masses, it is a genuinely extraordinary object whose existence is supported by direct spectroscopic evidence. And even if Phoenix A's true mass is significantly below 100 billion, it still inhabits an environment so extreme that it has no close parallel anywhere else in the observable universe. Neither object needs to hold a record to be remarkable. The scale they operate at is remarkable regardless of the ranking. The environment they inhabit is remarkable regardless of which one is heavier. The question of which is larger is, in a sense, the least interesting thing about either of them. What is interesting is what they tell us together. They tell us that the universe produces gravitational engines of such staggering mass that our best instruments can barely distinguish between them. They tell us that the familiar language of records and rankings, which works perfectly well for mountains and ocean trenches and ordinary galaxies, begins to fail when applied to objects measured in tens of billions of solar masses at distances measured in billions of light years. They tell us that the boundary between confirmed observation and careful estimation becomes thin and porous at exactly the point where the stakes are highest. And they tell us something else. Something that has been building quietly through this entire story and that demands its own space to breathe. They tell us that the universe does not care about our categories. It does not organize its most extreme objects into neat rankings for our convenience. It does not pause at the boundary of what we can comfortably measure and offer clarity. It produces what gravity and time and the initial conditions of a 13.8 billion-year-old cosmos allow, and it leaves us to sort out the details with whatever tools we can construct. The rankings will shift, the estimates will be revised, the leaderboard will continue to be redrawn in pencil, erased, and redrawn again. And through all of it, the objects themselves will remain unchanged, indifferent to our attempts to order them, sitting at the centers of their galaxy clusters and their quasar environments, feeding or dormant, growing or stalled, utterly unaware that a species on a small rocky planet orbiting an unremarkable star has spent decades trying to determine which one is the largest. The answer to that question is not what this story has been building toward. What it has been building toward is something stranger and more durable than any single number. Something that sits at the intersection of the scale of these objects, the limits of our instruments, and the question of what it means to be a thinking creature in a cosmos that produces things too large to rank, too distant to measure cleanly, and too extreme to fit inside the categories we build to make sense of reality. That is where we are going next, and the view from there is unlike anything we have encountered so far. There is a paradox waiting at the heart of everything we have covered so far. A paradox that most discussions of extreme black holes never reach because they stop at the numbers, satisfied that the scale alone is sufficient to produce wonder. But the numbers are only the surface. Underneath them, embedded in the physics of what these objects actually are and how they actually behave, there is an inversion of intuition so complete and so disorienting that it changes the nature of the fear these objects should produce. Here it is. The larger a black hole becomes, the gentler its event horizon feels to anything crossing it. Not metaphorically gentler, physically, measurably, quantifiably gentler. The tidal forces at the event horizon, the difference in gravitational pull between the near side and the far side of any object passing through, decrease as the black hole's mass increases. For a stellar mass black hole of 10 solar masses, the tidal forces at the event horizon are so extreme that any object approaching would be stretched along the radial direction and compressed laterally long before reaching the boundary. This process, which physicists call spaghettification, is violent and immediate. The gradient of gravity across a human body at that distance would be large enough to pull the feet toward the singularity with measurably more force than it pulls the head. The difference in acceleration would be experienced as a tearing force. There would be no ambiguity about what was happening. The approach to the event horizon of a stellar mass black hole announces itself. For M87 star at 6.5 billion solar masses, the tidal forces at the event horizon are dramatically weaker. An astronaut falling freely toward M87 star would cross the event horizon without feeling the tidal stretching that would destroy them near a smaller black hole. The gradient of gravity across a human body at that distance is small enough that it falls below the threshold of physical sensation. The crossing would be imperceptible. There is no announcement, no physical signal, no sensation of threshold, just the quiet, invisible, irreversible passage from a region of space-time where escape is possible to a region where it is not. For Phoenix A, at 100 billion solar masses, the gentleness at the event horizon is taken to an extreme that becomes almost philosophically troubling. The tidal forces at the boundary are so weak that not merely a human body but an entire planetary system could cross the event horizon of Phoenix A without any component of that system experiencing a detectably unusual gravitational environment. Stars could orbit each other. Planets could circle those stars. Moons could circle those planets. Life, if it existed on any of those worlds, could go about its existence entirely unaware that the region of space-time it inhabited had become a one-way passage from which no information could ever escape. The event horizon of Phoenix A is not a wall. It is not a surface. It is a region of ordinary seeming space that has, by the geometry of general relativity, become a point of no return. Every trajectory within it curves inexorably inward, regardless of direction or velocity. No engine, no matter how powerful, no structure, no matter how strong, could reverse the infall once the horizon is crossed. But there is no sign, no marker, no physical sensation at the moment of crossing. Nothing to distinguish the inside from the outside except the mathematical fact that escape has become geometrically impossible. Think about what that means. An entire civilization, if one existed in a galaxy, unfortunate enough to orbit within the event horizon of an ultramassive black hole, might never know its fate. Their physics would work normally. Their light would travel normally within the confines of the trapped region. Their telescopes would show them a universe of stars and galaxies and cosmic structure. The only thing they could not see, could not measure, could not detect by any local experiment is that the entirety of spacetime they inhabit is curved into a one-way funnel from which no signal they ever produce will reach the outside universe. They are inside, permanently, and the universe outside cannot tell them, because no signal from outside can cross the horizon inward either. Communication in both directions fails. The inside cannot reach the outside. The outside cannot reach the inside. They are separated not by distance but by geometry, by the shape of space-time itself. This is the predator that does not announce itself. The popular image of a black hole as a violent, crushing maw that destroys everything at its edge is accurate for stellar mass objects. For moderately supermassive ones, it is approximately right, but at the ultramassive end, the event horizon becomes almost serene. The violence is still there, the destruction is still guaranteed, but it is postponed, deferred, delayed until the infalling object has traveled deep into the interior, where the curvature finally becomes extreme enough to produce tidal forces that matter. For Phoenix A, that depth is vast. The interior of the event horizon spans thousands of astronomical units. An object falling freely from the horizon would travel for months, possibly years, before reaching a region where the tidal forces became physically significant. Bigger means gentler at the boundary. More massive means less immediately dangerous at the threshold. The largest black holes in the universe are, in a precise physical sense, the least alarming to approach and the most completely inescapable once entered. This inversion is not a quirk. It is a direct consequence of the mathematics of general relativity, which has been tested to extraordinary precision across a wide range of physical conditions and has never been found wanting. It is not speculation. It is a rigorous prediction of the best-tested theory in the history of physics, and it produces a conclusion that feels wrong to every instinct honed by ordinary experience. The thing most capable of consuming you is the thing that gives you the least warning that it is doing so. There is something in that inversion that resonates beyond the physics. It describes, in the language of geometry and gravity, a pattern that appears in other places where scale becomes extreme enough to break intuition. The most dangerous boundaries are sometimes the least perceptible. The most complete traps are sometimes the ones that look most like open space, and the most extreme objects in the universe are the ones whose extremity is least legible to anything passing through them. Now step back from the physics and consider what this entire story, from Sagittarius A-star to M87, star to Ton 618 to Phoenix A, has been building toward as a statement about knowledge itself. We began with a measurement, 4 million solar masses, confirmed by 3 decades of orbital mechanics applied to individual stars, cross-checked by 2 independent research groups, awarded a Nobel Prize. A number written in ink, Then we climbed to 6.5 billion solar masses, confirmed by stellar dynamics and an independent image-based measurement from the Event Horizon Telescope. Still ink, though the pen is slightly less fine. Then we climbed further to a range of 40 to 66 billion solar masses, derived from spectroscopic observation of orbiting gas, complicated by radiation pressure effects and the choice of spectral line. Pencil now, the range is wide. The method is sound but indirect. Then we reached 100 billion solar masses, derived from theoretical modeling of a galaxy and cluster environment, without direct dynamical measurement, with an independent estimate placing the true value potentially an order of magnitude lower. The pencil is faint here, the paper is thin. Each step up, the ladder carried a cost. The cost was certainty, and the rate at which certainty was spent accelerated as the mass increased, because the objects became more distant, the environments more complex, the methods more indirect, and the theoretical models more laden with assumptions whose validity could not be independently verified. This is not a temporary situation. It is not a problem that will be solved by the next generation of telescopes, though those instruments will help at the margins. It is a structural feature of the observational universe we inhabit. The most extreme objects tend to be the rarest. The rarest objects tend to be the most distant, because a larger volume of space must be searched to find them. The most distant objects are the hardest to characterize with precision, and the hardest to characterize are precisely the ones about which we most want definitive answers. The universe has arranged things so that the questions we care most about are the ones it is hardest to answer cleanly. This may not be coincidence. It may be a direct consequence of the fact that we are embedded in the universe, observing it from a single vantage point in space and time, limited by the speed of light, the sensitivity of our instruments, and the angular resolution achievable by telescopes built on a planet 8,000 miles in diameter, orbiting a star in the outer arm of a spiral galaxy, 26,000 light-years from its own modest central black hole. We are not outside looking in, we are inside, looking outward from a specific location through a specific cosmic epoch with specific tools developed over a few centuries of scientific civilization. The view from here is extraordinary. It has revealed a universe of breathtaking complexity and scale. But it is not a complete view. It is a view from one point, and at the extreme edges of what that view can reach, the image blurs. Priyamvada Natarajan's theoretical ceiling at 100 billion solar masses is a remarkable piece of work precisely because it makes a prediction that can in principle be tested. If the ceiling is real, no black hole should significantly exceed that mass under standard astrophysical conditions. If observations eventually reveal an object at 150 billion solar masses, confirmed through direct dynamical measurement, the ceiling would need to be revised upward or abandoned entirely, and with it, the models of feedback and accretion that produced the prediction. If no object is ever confirmed above the ceiling, it could be taken as evidence that the models are approximately correct. But here is the difficulty that haunts this test. If Phoenix A's true mass is near the ceiling, and we cannot confirm it through direct measurement, and if no other object is measured above the ceiling because no other object exists above it, then the ceiling remains simultaneously predicted and unverified in practice. We cannot confirm that nature reaches the limit because we cannot measure the most extreme candidates with sufficient precision to place them confidently at the limit. We cannot rule out that the limit is lower than predicted because we cannot rule out that our best estimates are overestimates. The theoretical prediction and the observational test are separated by a gap that current technology cannot bridge. This is not the comfortable situation of a theory awaiting confirmation that everyone expects will arrive within a generation. It is the more unsettling situation of a prediction that may be correct, may be approximately correct, or may be subtly wrong, with no clear path to distinguishing between those possibilities using instruments that will be built in the foreseeable future. And this is where the deeper philosophical dimension of the ultramassive frontier becomes impossible to ignore. We are accustomed to thinking of science as a process that converges on truth. Given enough time, enough data, enough ingenuity, the right answer emerges. The history of physics is full of examples. The orbit of Mercury, anomalous for decades, explained by general relativity. The cosmic microwave background, predicted theoretically, detected accidentally, now mapped with extraordinary precision. The existence of gravitational waves, predicted by Einstein in 1916, detected directly in 2015 by the LIGO collaboration. The image of a black hole's shadow, theorized for decades, produced in 2019. In each case, the question was answerable and eventually answered. Patience and ingenuity were sufficient. But the ultramassive black hole problem presents a different character of difficulty. It is not a case where the answer exists clearly in the data and simply needs better analysis. It is a case where the answer may exist in data that is in principle observable but is, in practice, so diluted by distance and complexity and contamination from intervening processes that no realistic instrument can recover it cleanly. The signal exists, but the signal-to-noise ratio is not merely low. In some cases, it may be fundamentally, irreducibly low, given the physics of how light propagates across 10 billion light-years of expanding space. Some truths may be permanently blurred, not because the universe is hiding them deliberately, not because there is anything philosophically special about the limits of knowledge, simply because we happen to exist at a particular location and time, observing with instruments of finite capability, in a universe where the most extreme objects are also the most remote, and where the most remote objects return the least information about their most extreme properties. This is a possibility that science is not always comfortable acknowledging, because the narrative of scientific progress is so strongly shaped by the experience of problems that eventually yielded. The geocentric model yielded, the static universe yielded, the impossibility of directly imaging a black hole yielded. Each apparent limit was eventually surpassed. The story of science is a story of limits overcome. But not every limit is of the same character. Some limits are technological and yield to engineering. Some are theoretical and yield to new frameworks. And some are geometric, rooted in where we are in the universe, and what that position allows us to see, and those yield to nothing. The cosmic horizon, the boundary beyond which the universe has expanded so fast that light from those regions can never reach us, is a limit of this third kind. We cannot observe beyond it regardless of the quality of our telescopes or the sophistication of our theories. The ultramassive black hole problem may not be a limit of this absolute kind, but it may be closer to it than the history of scientific optimism would suggest. The angular size of a black hole sphere of influence at 5.7 billion light-years, or 10.8 billion light-years, is not merely below current resolution limits. It is below resolution limits that can be improved by building larger telescopes on the ground. It approaches the regime where the only way to achieve sufficient resolution is to place telescopes in space, separated by distances comparable to the Earth-Moon distance or larger, and to process the resulting data with algorithms of extraordinary complexity. Such instruments are conceivable. They are not currently funded, not currently designed in sufficient detail, and not on any near-term roadmap of space agencies. They represent a level of ambition beyond anything currently planned for the next several decades, which means that the question of whether Phoenix A truly reaches the theoretical ceiling, the question of which ultramassive black hole genuinely holds the mass record, may not be answered within the lifetimes of the scientists currently asking it. There is something clarifying about sitting with that uncertainty rather than resolving it prematurely. Most stories about extreme objects in the universe end with a number. The largest black hole is this, the most luminous quasar is that, the most massive galaxy cluster weighs so much. The numbers are real and they matter, but they are also incomplete in a way that rarely gets acknowledged in the popular telling, because the popular telling wants resolution. It wants the record holder crowned. It wants the champion identified. It wants the story to end with a fact rather than a question. What Phoenix A and TON 618 together reveal is that the honest ending to this particular story is not a number, it is a description of a boundary. A place where the tools of science reach their current limit, where the most extreme objects resist precise characterization, and where the ranking of the cosmos's most massive inhabitants remains genuinely, irreducibly uncertain, not because anyone failed, not because the science is incomplete in a way that reflects poorly on the people doing it, but because the universe is arranged in a way that places its most extreme creations at distances and in environments that are among the hardest to read. The leaderboard at the top of the black hole mass scale is written in pencil. The pencil is wielded by some of the most skilled scientists in the world, using some of the most sophisticated instruments ever built, applying some of the most carefully tested physical theories in the history of human knowledge. The writing is as good as it can currently be, but it is still pencil, and the eraser is always within reach. There is a question that has been sitting at the center of this story since the first sentence. You heard it stated at the beginning, before the numbers began their escalation, before the methods were examined, before the gap between measurement and estimation became clear. The question was simple. It sounded like the kind of question that should have a clean answer. A name, a number, a champion. What is the largest black hole ever found? You are not the same person who heard that question at the beginning. The journey between then and now has changed what the question means. It has not answered it in the way you might have hoped. It has done something more lasting. It has shown you why the question resists the kind of answer it seems to demand, and why that resistance is not a failure, but a revelation about the nature of knowledge. Let us return to it now, not to finally crown a winner, but to stand before the question with everything the journey has given us and see what it looks like from here. The largest black hole we have found is probably Phoenix A. That is the honest summary of where the evidence currently points. Its estimated mass of 100 billion solar masses exceeds every other serious candidate in the literature. It sits in an environment uniquely capable of producing an object of that scale, a catastrophically cooling galaxy cluster where the thermostat failed and the central black hole fed without adequate constraint for billions of years. The physical scenario that produced it is internally consistent, grounded in real observations, and supported by a convergence of independent lines of evidence that all point towards something extraordinary at the center of that cluster. The theoretical ceiling derived from models of black hole growth, feedback, and the Eddington limit places the maximum achievable mass at approximately the same value the estimates assign to Phoenix A, which either confirms that nature can reach the limit or suggests that the estimate has landed near a theoretically convenient number by coincidence or by the influence of modeling assumptions that were themselves calibrated against theoretical expectations. TON 618 is the most observationally grounded of the extreme candidates. Its mass, somewhere between 40 and 66 billion solar masses, rests on direct, spectroscopic measurement of gas orbiting in its gravitational field. The method is less direct than tracking individual stellar orbits, but it is fundamentally observational rather than model-dependent. The quasar's extraordinary luminosity, 140 trillion times that of our Sun, visible across 10.8 billion light-years of expanding space, is itself evidence of a central engine of staggering scale. And the Lyman Alpha Nebula surrounding it, 3 times the diameter of the Milky Way, is a physical record of the black hole's influence written across space in hydrogen gas. TON 618 may not hold the record, but it holds something arguably more valuable in the currency of science. It holds the clearest direct evidence. Both objects are real. Both are extreme beyond any comfortable human analogy. Both press against the limits of what our methods can characterize and what our intuition can absorb. And between them, they define the frontier of what we currently know about the most massive objects the universe has produced. That frontier is not a line. It is a region, a zone where knowledge shades into estimation, where estimation shades into modeling, and where modeling eventually gives way to the vast dark of what we have not yet measured and may not be able to measure with any instrument we currently plan to build. Step back further, farther than any telescope has looked, farther than any number in this story has taken you, not in space but in perspective, and consider what it means that this conversation is happening at all. Somewhere on a small rocky planet, orbiting a yellow dwarf star in the outer reaches of a spiral galaxy, a species that has existed for an eye blink of cosmic time has looked outward across 5.7 billion light-years and found an object so massive that its event horizon swallows a volume of space larger than the planetary system that species calls home. The same species has looked 10.8 billion years into the past, to a time when the universe was barely a fifth of its current age, and detected a gravitational engine shining with the light of 140 trillion suns. It has measured the cooling rate of gas in a cluster 2 quadrillion solar masses in size. It has imaged the shadow of an event horizon 55 million light-years away. It has tracked the orbit of a single star around an invisible mass for 30 years and used 400-year-old mechanics to calculate the result to within a few percent. None of this was inevitable. There is nothing in the laws of physics that required a species capable of doing these things to evolve on any particular planet. There is nothing in the structure of the universe that demanded the emergence of creatures who would look up at the night sky and not merely see it, but measure it, model it, argue about it, build instruments of extraordinary delicacy to study it, and then sit together in the knowledge of what those instruments revealed and feel the weight of what they could not yet determine. We are, as far as we know, the only things in the observable universe that know any of this. That is not a comfortable position. It carries a weight that the numbers themselves do not fully capture. The black holes do not know they are large. The cluster does not know it is extreme. The quasar does not know it is luminous. None of the objects in this story have any awareness of their own existence, let alone of the extraordinary properties that make them remarkable to us. They simply are what they are, products of gravity and time and the initial conditions of a universe that has been running its physics without interruption for 13.8 billion years. We are the part of the universe that notices, and what we notice when we look at the ultramassive frontier is that the cosmos produces things that exceed our ability to fully characterize them, not slightly, not in ways that a modest increase in telescope aperture will resolve. Fundamentally, irreducibly, perhaps permanently at current levels of technological ambition, the largest black holes in the universe exist at the intersection of extreme mass, extreme distance, and extreme environmental complexity, precisely the intersection where our methods perform worst. It is as though the universe has placed its most extreme creations behind the thickest glass. There is one more thing to hold before this story ends. Throughout every step of this journey, there has been an assumption embedded in the framing of the central question. The assumption that the largest black hole is one we have already found, that the record holder is among the candidates currently in the literature, Phoenix A or TON 618 or one of the other ultramassive objects that have been measured and catalogued and debated, that the survey of the extreme end of the mass distribution is complete enough that the true champion has already been detected. This assumption may be wrong. The observable universe contains an estimated 2 trillion galaxies. The surveys that have identified ultramassive black hole candidates have examined a tiny fraction of that number in the necessary detail. The most extreme objects are, by definition, the rarest, and rare objects are found last. The surveys are incomplete in ways that are difficult to quantify precisely, because the incompleteness is not random. It is biased toward nearby, bright, well-studied objects, and away from distant, faint, obscured ones. The most massive black hole in the observable universe may sit in a galaxy cluster we have not yet observed at sufficient sensitivity. It may be embedded in an environment so extreme that it has not yet been identified as a priority target. It may be dormant, its accretion disk cold and quiet, producing none of the radiation signatures that typically flag extreme black holes for detailed follow-up study. The record may not have been found yet, and if it has not, when it is found, it will almost certainly be found not by a sudden dramatic discovery but by the same slow process that brought us Phoenix A and TON 618, a faint signal in a survey. Follow-up observations across multiple wavelengths, careful modeling, a mass estimate with substantial uncertainties, a paper published in a scientific journal, a debate in the community about which method to trust, a number that sits in a range rather than at a point, a candidate rather than a confirmed champion. This is how the frontier advances. Not in sudden leaps, but in the gradual accumulation of uncertain knowledge, each piece of it incomplete, each estimate provisional. the picture sharpening slowly through the accumulated effort of thousands of scientists across decades of work. The advance is real. The knowledge is genuine, but it is always knowledge with error bars, always understanding that acknowledges its own limits, always a map that marks, with unusual honesty for a map, the regions where the cartographers have not yet gone. Return now to the Phoenix cluster, 5.7 billion light-years away, a gravitational colossus weighing 2 quadrillion solar masses. At its center, a galaxy where 740 new stars are born each year in a starburst fueled by the catastrophic failure of the thermostat that keeps most similar systems in equilibrium. And at the center of that galaxy, something that the best available models say weighs approximately 100 billion times the mass of our Sun. Something whose event horizon, if the estimate is correct, spans 4,000 times the distance from the Earth to the Sunday. Something whose gravitational influence rivals the total stellar mass of our entire galaxy. We do not know exactly how massive it is. We know it is extraordinary. We know the environment it inhabits is unlike almost anything else we have found in the observable universe. We know the physics that produced it is internally consistent and grounded in real observations. We know that it presses against the theoretical limit of how large any black hole can grow in the age of the universe under standard conditions. And we know that confirming its mass with the directness and precision that the question deserves is beyond the reach of any instrument currently available or planned. That is where we stand, not at the end of the story, at the edge of what the story can currently tell us. The rest waits in the data that future instruments will collect, in the theoretical frameworks that future physicists will develop, in the debates that future scientists will have over better measurements of objects that are currently characterized only approximately. The story is incomplete, not because it has been told poorly, but because the universe has arranged things so that its most extreme chapters are also its hardest to read. You began this journey thinking you were going to learn which black hole holds the record. You have learned something more unsettling and more durable. You have learned that the record itself is uncertain, that the leaderboard is written in pencil, that the most extreme objects in the cosmos resist the clean characterization that records require, that the boundary between what we know and what we estimate is not a wall but a gradient, growing thinner as the masses grow larger and the distances increase and the environments become more complex. You have learned that the largest black holes produce the gentlest event horizons, that the most complete traps are the most imperceptible, and that an entire civilization could be consumed by Phoenix A without any of its members ever knowing they had crossed a threshold from which return was impossible. You have learned that human cognition and scientific instrumentation reach their limits at the same place, that the numbers grow large enough to numb both the mind and the measurement, and that this convergence is not a coincidence, but a structural feature of what it means to be a finite observer in an infinite universe. And you have learned that the universe produces objects so extreme that even our best tools for measuring them begin to strain. That some questions about the cosmos are not temporarily unanswered, but may be permanently blurred by the geometry of where we stand and the physics of how information travels across the space between us and the things we most want to understand. All of that is real knowledge, hard-won, carefully qualified, honestly uncertain knowledge. The kind of knowledge that does not make headlines but does something more valuable. It tells you the true shape of the frontier. It marks not only what is known, but where the known ends and the estimated begins, and where the estimated fades into the vast dark of the not yet reached. The largest black hole ever found may be Phoenix A. It may be something we have not yet found. It may be a question that resolves into clarity within a generation, when new instruments achieve what current ones cannot. Or it may be a question that remains at the edge of the answerable for a very long time, pressed against the limits of what can be known from where we are, in this epoch, with these tools, in this universe. Either way, the scale is real. The objects are real. The cooling flow raining down onto that central galaxy at 3,000 solar masses per year is real. The starburst is real. The event horizon, whatever its precise diameter, spans a region of space that makes our entire planetary history look like a single grain of sand on a beach that stretches to the horizon in every direction. And somewhere out there, in the southern sky, 5.7 billion light-years away, At the center of the most extreme galaxy cluster we have ever found, something sits in the darkness and waits, not aware of its own immensity, not aware of us, simply present, as it has been present since before our sun existed, feeding on the catastrophic infall of material that its own broken thermostat cannot stop, growing perhaps still, crossing the theoretical ceiling of what the universe permits, or sitting just below it in a range our instruments cannot yet resolve. It does not know we are watching, it does not know we are here, but we are, and that in the end is the most extraordinary fact in this entire story. Not the 100 billion solar masses, not the 4,000 astronomical unit event horizon, not the cooling flow or the starburst, or the Lyman Alpha Nebula 3 times the width of the Milky Way. The most extraordinary fact is that a species of upright primates on a small wet planet has looked across 5.7 billion light-years of expanding space and found it, has measured it, modeled it, argued about it, and sat with the honest uncertainty of not being able to confirm it as cleanly as the question deserves. We are the part of the universe that looks back at itself and wonders. That is temporary. Everything is temporary at these scales. Our sun will exhaust its fuel, our galaxy will merge with Andromeda. The stars will eventually go dark as the last of the available hydrogen is consumed. The universe will cool toward a final equilibrium, in which the black holes themselves, even the ultramassive ones, will slowly evaporate through Hawking radiation across timescales so vast that the current age of the universe is not even a rounding error in comparison. But right now, in this moment, in this thin sliver of cosmic time, there are creatures here who can look at a point of light in the southern sky and know, within the honest limits of what knowing means at these distances, that it marks one of the most extreme objects the universe has ever produced. The darkness stretches farther than light, has traveled since the beginning of time, and somewhere inside it, we are still looking.